Okay, I think we'll get started. So today we are taking a little interlude here to talk about something called Hess's law. So this brings us back more to the auxiliary functions of thermodynamics that we've talked about earlier, and it allows us to utilize some of those properties, in particular the fact that they're state functions, to build a reaction that Mother Nature does one way. We can do it by taking any path of reactions. As long as we start with the reactants and end with the products, we don't have to take the sequence of reactions that Mother Nature does, and we can still get the thermodynamic values for that reaction. Okay, so let's consider a generic reaction, and this will be some thermodynamic function, H, S, or G. We could use U, but we usually don't in general chemistry. So here's our delta G, for example, standard, delta S standard, or delta H standard for this reaction as written. Now we've talked about before that if we multiply the stoichiometry by some value, then we multiply the thermodynamic function by that value. So if we double all the stoichiometric factors, we double the thermodynamic value. We didn't talk about this before, but if we turn the reaction around, so we're free to turn the reaction around, then that simply negates the value. That should be a standard. Negates the value of the thermodynamic property. Now, these are all state functions. If we remember what a state function is, state function means that it's independent of the path of how we get from one state to another. So the state is this and this, products and reactants. That's what we'll call the reaction, right? The direct reaction. But if we take a sequence of reactions, so in this case, this example 4, but any number, if we sum over all of those, then that gives us the thermodynamic value. And this is called Hess's law. Hess's law. Now, there's a very special case of this with what are called formation reactions. And although these reactions often don't happen in nature very readily, what they are is the reaction for forming some molecule from its elementary components. So for example, the formation reaction for water would be the formation of exactly 1 mole of water. So let's see, let me do it. Let me just erase this. So the formation reaction for water would be 1/2 H plus OH minus goes to H2O. And this would be a gas, and it does matter here if it's gas or liquid. We'll say liquid. Well, the delta H for that, of formation, so delta H of formation, for example, is minus 285.8 kilojoules per the 1 mole. Right, so here's the reaction. Normally the reaction is just in kilojoules, not kilojoules per mole, but when it's a formation reaction, we are precisely forming 1 mole, so kilojoules per mole. Carbon dioxide would be, for example, carbon solid plus oxygen gas goes to CO2 gas. And that the delta H for that, the delta formation H, is minus 393 kilojoules per mole. Minus 393.5 kilojoules per mole. So what we can do is we can combine this with Hess's law. And this makes a very systematic way of getting the delta G, delta H, or delta S for any reaction as long as we already know the values for the formation reaction. And these huge tables of formation reactions that you can look up in handbooks or online. And because we know so many of these formation reactions, we can put together a vast amount of reactions and get the appropriate standard thermodynamic properties for that reaction. So how we do it is we simply take and add up all the products, add up all the reactants, and then take products minus reactants. Okay. So let's do an example of this. Let's say we have this reaction. So this happens to be butane. It's a gas, and it can combust in oxygen to form carbon dioxide and water. Let's say we want to get the delta H for this. We want to get that. Well, we take and we collect all the species present. This is supposed to be, it's like a parentheses, but it's a carbon. So butane, 1 mole of butane, 1 mole of oxygen, 1 mole of carbon dioxide, 1 mole of water. Okay. Here are these numbers I had before. These are the formation reactions for 1 mole of water, 1 mole of carbon dioxide. Oxygen is already in its natural state, so the formation, it is its own element, so formation reaction is 0. And then butane, the formation reaction happens to be minus 127 kilojoules per mole of butane. So then we take the reaction as written and we ask ourselves, well, what are we forming? 8 moles of this and 10 moles of this, and where are they coming from? 2 moles of this and 13 moles of that. So we have to take 8 times this plus 10 times this minus 2 times this minus 13 times this. So we take 8 times CO2, right? So 8 times minus 393 plus 10 times minus 285 minus a 2 times a minus 127 plus 0, because we have 0 here. And when we do that, this all adds up to 557.52 kilojoules. Now this is not kilojoules per mole. This is kilojoules for the reaction as written. So if we divided this by 2, then we would have to divide that by 2 as we know to do. Okay, so some subtleties here. The formation reactions are given to us as kilojoules per mole because we're forming exactly 1 mole. We multiply them by the moles in the stoichiometry, so that cancels that mole unit and leaves us just with kilojoules. Now, let's do another example, not with formation reactions, but just a general Hess's law example. So let's take this molecule, happens to be niacin, and let's react it with ammonia. So we're going to take niacin plus ammonia, and it will form this conjugate base to this and ammonium ion. And we want to know what's the delta G for that. Well, let's say we know this reaction. Okay, let's say we happen to know this reaction. Right? So we just happen to know this reaction. We don't know this reaction, but we know this reaction. We know this reaction. And we know this reaction. So Mother Nature takes the top reaction. We know these bottom 3 reactions. And now let's just think of this as a mathematical equation, and we're going to add these reactions. So I want this for sure, right? And I want this. And then I want this for sure. And I want this. But I don't want anything else. So if I take and add these 2 reactions, I certainly have what I want, right? But I also have water. So I have this, this, and this if I were to add these together. And I don't want those. So I need to add in another reaction. I need the water dissociation reaction in reverse. And so when I add all of these, I can get this on this side, this on this side. That will cancel. This will cancel, and this will cancel. So just line up all your reactions, cross out the ones that are on both sides, and then hopefully you have the reaction that you're interested in. If you do that, and you know the thermodynamic values for these reactions, then you simply add them together, right? It's not products minus reactants like over here. We simply add these together. So minus 276.9, minus 270.7. Yeah, plus, yeah, and then plus this. So 251 kilojoules. Just kilojoules. And so that's our delta reaction G for this. Okay, well, I'm going to let you be largely on your own, and this is all I'm going to say about this. Every general chemistry book you have will have a section on Hess's law, and that will include the heats of formation. There'll be a nice appendix in your book, no matter what book you have, that has the formation reactions in them, standard formation reactions. So you should practice a few of those. We're not going to worry too much about that as is, although it's a critically important thing for anybody doing chemical thermodynamics. We're just not going to say too much about it. So you're sort of on your own for that. Let me just do one last thing before finishing here. Let's look at this delta G here. So let's say I have a single reaction. We'll call this reaction 1. And that has a particular delta G, delta reaction G, standard. Well, we know that that is minus K, minus RT ln K. Minus RT ln K. Yeah, okay. Sorry, I have a mistake over here. As I wrote that minus RT ln K, see, these, let's correct these. These are plus plus minus. And so that should be a minus 251. Sorry about that. I had got these values from K's, and I'm started to get suspicious here because this reaction should go forward, and we got a positive delta G, which was telling me that that should go backwards, which is not the case here. So this should be minus 251 there. Okay, so here's our reaction. Let's call this reaction 0, and this is going to be made up via Hess's law. Let's just do reaction 1, reaction 2, and reaction 2. That's enough. So this has a delta reaction 1 G, and this is a minus an RT ln K1. And this has a delta reaction G2 of a minus RT ln K2. Okay. So if we add these two, then we get reaction equals reaction 1 plus reaction 2. That's a Hess's law statement. And then minus RT ln K equals minus RT ln K1 plus minus an RT ln K2. And I can cancel out a minus RT, and then I can use property of logs. So log of K equals log of K1 times K2. And then I can exponentiate both sides. So K is product. And so this is how Hess's law carries itself through to the equilibrium constant. If we're adding reactions, we're multiplying the K's. If we turn a reaction around, we have to subtract the reaction. Then we would be dividing the K's. And so Hess's law plays itself out through to the equilibrium constant as well. All right, and this is what we'll be using. We'll be using this delta G's, and really in the form of delta K's, when we react weak acids with weak bases. And so that's the reason for this interlude on Hess's law, is so it'll give us a bigger capability to handle a wider variety of acid-base reactions. Your general chemistry book will only handle strong acids reacting with weak bases, or strong weak acids reacting with strong bases, but it will not cover the weak case. And so we want to be able to handle the weak case, and so we need this for that. All right, so we'll get back to the acid-base chemistry in the next lecture.